Hello, and welcome to Types of Functions and Their Representations. This will be a college algebra view of the subject. Let's start with the definition. A function f, represented by f of x equals b, where b is a constant, so a fixed number, is called a constant function. Constant functions are easily recognizable by their lack of variable in the rule, so in the right-hand side. Yeah, there's a variable over here in the name of the function, but not in the rule. A function f represented by f of x equals mx plus b, where m and b are constants, is called a linear function. Linear functions have a constant rate of change, so the difference between consecutive output values will always be the same value, m. All right, so the slope, m, of the line passing through the points x1, y1, and x2, y2 is given by m equals delta y over delta x. This delta is a Greek letter for change in, right? In math, delta means change in. So the change in y divided by the change in x. And that's y2 minus y1 over x2 minus x1, right? Change in y divided by the change in x. Of course, x1 and x2 cannot be equal, or else we'll have a 0 in the denominator and bad things happen. What can happen with our four types of graphs from linear functions themselves? From linear functions, we could have a slope of 0, which is a horizontal line. Wow, L-I-N-E. Ooh, that was rough, wasn't it? We could have a negative slope. The negative slope will always fall from left to right, whereas a positive slope linear function will always rise from left to right. And our last one is a vertical line. And this vertical line is when x1 is equal to x2 and we say that m is undefined, because we cannot divide by 0. It goes back to that same idea. So a vertical line is not actually a linear function, but if the x values are the same, a vertical line is frequently associated with linear functions because it is a line, right? But is not a function, right? It does not pass any type of function rules here. If the input is -1, it has an output, an infinite different number of outputs for one input, so that's not going to be a function. All right, using our formula here at the top of the page, we can find the slope of a line passing through 4, 6, and 2, 5. In order to find my slope, I'm going to subtract y values, and then I'm going to subtract x values in the same order. Since I started with the 5, I start with the 2 in the denominator. 5 minus 6 is -1. 2 minus 4 is -2, and when we simplify this fraction, we'll get a slope of 1/2. Remember, negative divided by a negative is positive. All right, now how are we going to actually use this in real terms? The distance d in miles that a train is from a station, x hours, after x hours, I can't even read my own typing, is given by the formula d of x equals 150 minus 20x. So calculate d of 6 and interpret the results. Well, d of 6, d of anything, is 150 minus 20 times that thing. In this case, we want to use a 6. So we can evaluate d of 6 to find 150 minus 120 to get an answer of 30. 30 what? 30 miles. Units are always a good thing to include. D of 6, interpret the results. After 6 hours, right, that was our input. The train is 30 miles from the station. One of my rules is, if it starts with words, you should finish it up with words, right? Your answer should be answered back in words. So however a problem starts, that's what you should use to answer it. Find the slope of the graph of d. Interpret the slope as a rate of change. Well, our slope is always going to be this coefficient, right? This coefficient of the linear variable. So our slope is negative 20. But what does that mean as a rate of change? Well, slope is output, miles, divided by input per hour. So the train is approaching OACH. Let's see if I could spell this. The station at 20 miles per hour. Now, why did I say approaching? This negative 20 tells me I'm getting closer to the train station. All right. This actually says I'm closing down the distance. The distance is getting smaller, so that tells me I'm approaching. If it were positive 20 miles per hour, the train is leaving the station at 20 miles per hour, is getting further from that sort of response. All right, so approaching takes care of our negative, and 20 miles per hour takes care of the rest. There we go. So let's let f be any function. Then any number c for which f of c equals 0 is called a zero of the function. We also call these roots. We call these intercepts. Let's say it correctly though. They are x-intercepts. They are roots, zeros. Zero is a great name for it because it's where the function is 0. So let's look at this graph. Right? It seems to have nothing to do with the previous definition, but I'm promising myself that it does. If we graph f of x equals 3x2 by hand, let's start with the y-intercept at 2. And then we'll use our slope of 3. If m equals 3, that's the same as 3 over 1. So we'll go up 3 over 1 and find a new point. All right, so when I draw this graph in here, oh yeah, I even hit the points. I was able to identify the slope. I can identify the y-intercept. And from here we can see that we will have an intercept here, and our y-intercept, our b value is going to give us our y-intercept, whereas here in black I have our x-intercept. It's a 0. All right, so this is where our 0 happens. It's where the function, the y values, are equal to 0. All right. Let's look at another example. This is going to be the last example of this part of the lecture, I believe. I don't know, I might make this a full video instead. A graph of a linear function is given. All right, here it is. There's the graph. I want to identify the slope, the y-intercept, and the x-intercept. I want to write a formula and estimate the 0. That should be pretty easy. Let's see. First, we look at the slope. I'm going to take any 2 points that cross at a nice grid mark. There's one and there's one. Now in order to get from the point on the left to the point on the right, I'm going to go up 2. So I'm going to write that there, up 2. And then I'm going to come over 3. To the right 3. So my slope is a positive 2/3. I can find my y-intercept, happens to be right here. My y-intercept b is at the point 0, -2. It's not actually b. b is -2, but we call it a point, so we always label it. Throw an arrow on it instead of an equal sign, it'll be all good. And our x-intercept, where does it cross the x-axis? That's right here. That's our x-intercept. Our x-intercept is at the point 3, 0. All right, so lots of 2's and 3's going on in this example, but it's the problem I picked. So if I want to write a formula, think about how straightforward this is now. I know it's a formula, it's a function. I know my slope is 2/3 mx plus b. And because b is a negative, I am going to use minus 2. So we could write a formula for that really quite easily. And if I wanted to estimate the 0, it is the x-intercept. So I could estimate that pretty easily by having 3, 0 as my x-intercept. So 3 is a 0 of f. All right, so it's all in the interpretation. X-intercept is a point. 0 is just a specific number. X equals 3 gives you the 0 of f. I changed my mind yet again. I am a woman. Watch me change my mind. Women embrace it. Men get used to it. That's it for part 1 of types of functions and their representations. Stay tuned for part 2.